So I'm going to start with the brief recall of Gauss's law. It is so important. I wanted to make sure you guys understand not only how it is used, but how it's derived. I derived it for you last time, but I thought it could be, presentation could be improved a little bit. So I'm going to do it one more time. Just this time only hitting the highlights. The content of Gauss's law is very easy to visualize. So I'm going to draw you a picture that will tell you the whole story. Then there are all the equations. Picture is the following. You take one charge, Q, and you draw the lines of force coming from the one charge. It's a point charge. Therefore, you have no freedom but to draw lines that look like this. Now, how many lines you draw is a matter of convention. You can draw 8 or 12, whatever it is, but you got to agree that the number per coulomb should be fixed. So we'll pick some number. So I'm going to pick for whatever charge is here, these lines. You cannot have a distribution of lines in which it's suddenly more dense in just this direction, for example. That's not allowed, because if I take this point charge and I rotate it, it looks the same. But if I took the line distribution with more dense here than other places, if I rotate it, it looks different. So if the cause of the field lines looks the same after rotation, the effect, which is the field lines, should not change. So you can only have a distribution of lines which respects the symmetry of the source or the cause of the field lines. You understand that? It cannot be biased one way or the other, whereas this distribution, if you turn it around, looks exactly the same. So we draw those lines, and the content of Gauss's law is really the following. We are going to count the lines crossing a sphere S, and we're going to count the lines crossing some generic surface S prime. Now you can see at a glance, without doing any calculations, that the following is true. Lines crossing S equals lines crossing S prime. Right? That's clear to everybody. You don't need to do any equation for that. That's because the lines have nowhere to go but out, and you can count them on this circle, that circle, as long as you enclose the whole thing, the solid surface enclosing this charge, you're going to get the same lines. That's the heart of Gauss's law. But that's not the final form, but that's the part that starts everything. Now I'm going to calculate the left-hand side, and I'm going to calculate the right-hand side. I'm going to equate them. And from that, I will get almost everything I want. Now, how many lines are coming out of S? We know, first, the notion of line density. I got to remind you what a line density is. Line density is the lines per area, but it's not enough to say area. I'm going to put a perpendicular symbol there. That means if the lines are going, say, from left to right, like this, you want to put an area that intercepts it perpendicularly. Or if you like, the area vector, which is always normal to the area, should be parallel to the lines. So it's the number of lines crossing unit area perpendicular to the lines. That's called the line density. If you tilted this area, the same area but at a bad angle, it will intersect fewer lines. That you know. Okay, so this is the meaning of line density. What's the line density going to look like in this problem? Line density is going to be proportional to the charge you have, because we agreed. We will put some number of lines per coulomb, and it's inversely proportional to the radius, because the area of a sphere of radius r is 4 pi r squared. So if you cut it with a bigger sphere of bigger radius, the density, lines per area, will go like 1 over r squared. So it's proportional to Q. It's proportional to 1 over r squared. Okay? So let me write it not equal to, but proportional to. You have to stop me if you don't follow anything I'm saying. There's no reason why you shouldn't follow this argument. Then I say, how about the electric field? The strength of the electric field, not the direction, the electric field E at radius r is also proportional to Q and also proportional to 1 over r squared. Because from Coulomb's law, the field is the force on a unit test charge. It is Q1 times Q2. Q2 is 1 because the test charge is 1, and it's Q over 4 pi epsilon 0 r squared. Forget the 4 pi. It's proportional to Q over r squared. From this, we may conclude that the line density is proportional to the electric field because they are both proportional to Q over r squared. Therefore, we can say line density is equal to some constant c times the electric field in magnitude. Direction of the lines is along E, but the magnitude, do you understand that? This guy is proportional to this. This may have some proportionality constant, this may have another one, but nothing changes the fact that this expression is proportional to that one. The constant will depend on details. Let me just call it some number c. C is up to you. It really depends on how many lines you want to draw per Coulomb. I made a particular choice last time, 1 over epsilon 0 lines per Coulomb, but you don't have to make that to prove the law. So this time, I'm just assuming the lines is proportional to charge, but you pick your own proportionality constant. So I've got this line density is proportional to electric field. Now I'm going to go back, and I'm going to calculate the left-hand side. Now let's give this equation a number. Equation number 1. I'm going to calculate the left-hand side of 1. Left-hand side of 1 is the number of lines crossing the sphere S. So that's going to be equal to, let me call it phi sub S is equal to number crossing S, crossing the sphere S. Phi is a standard symbol for flux. So what is it? Well, phi sub S equals line density times area of sphere. Because on a sphere, the lines are uniform in density, so the total number crossing the sphere is the line density times area of the sphere. But the line density is a constant times the electric field at radius r, if you like, times area of a sphere, which is 4 pi r squared. That's the lines crossing the inner surface, which is the sphere of radius r. Now, phi sub S prime is lines crossing S prime. Now, you've got to be a little careful when you find the lines crossing S prime. You understand why that's more difficult? What are the two complications in finding the lines crossing S prime compared to this one, which I did in 1 second? Any idea? Yes?
Those are all parallel to the field lines?
Which is not parallel?
The normal to the surface isn't parallel.
Okay, the surface is not, surface vector at each point is not parallel to the electric field. For example, if you got a crazy surface like this, I'll try to replicate that surface, but I don't remember what I drew, some weird object like this, then the electric field point this way, but the normal to the surface will point that way. See, E points that way, tiny area there, which I'm calling vector dA, points in a different direction. So each region has a different direction. Secondly, the strength of the field itself is varying on the surface. Unlike on a sphere where everything is at same distance r, some are further, some are closer. But it is still true that if you want the number of lines crossing a path, if you pick a little area here, If you want to know how many lines cross that, you take the normal to the area, call it a vector dA, and you multiply by line density. Therefore, this is equal to the integral of the electric field at some point r dot product with the tiny area which is there. At each region, you got to draw a different dA. So you take the surface, you chop it up into tiny little tiles. Each tile is small enough to be considered a plane. Then the area vector is perpendicular to the plane, outward from the surface, and of magnitude equal to the numerical area of the plane. So the lines crossing every tiny little square on that big surface is the number of lines per unit area times the area times the cosine of the angle which you need, because the area vector may not be parallel to the flow. I've explained many times why if the flow vector and the area vector are not parallel, you got to put in a cos theta. That's what comes in to this dot product. And we write a symbol like this to tell you not only is it a double integral, meaning integral over a two-dimensional region, but it's over a closed two-dimensional region. That symbol is to remind you. So now, phi sub s equal to phi sub s prime is what I'm going to write. So I'm going to write, oh, I made one mistake. Can anybody see one thing missing in this equation here? This equation is not correct. To find the lines crossing x prime, I took E times dA. It's a constant C, because the line density is not simply the electric field, it's the constant. So I forgot the constant, but I knew that I would need it, because when I now equate phi sub s to phi sub s prime, I get constant times the electric field at r times 4 pi r squared is equal to constant times the surface integral of E dot dA on some surface S prime. But ER times 4 pi r squared is C times Q over epsilon 0, because E is Q over 4 pi epsilon 0 r squared. You see that? This much you should know. I'm not going to write the details. So that is equal to C times surface integral of E dot dA. Now you see the constant does not matter. So whatever the constant is, I can make the following statement, and that's going to be the beginning of Gauss's law. So Gauss's law tells me that if you took a charge and you surrounded it with any surface whatsoever, I'm not going to put a prime on this anymore. S is going to be the surface. Then the surface integral of the electric field due to that charge over a surface is equal to the charge that is sitting inside divided by epsilon 0. And it does not depend on the details of the surface.
Okay, good morning. I will pause that video or stop that video. Okay, so that is a very brief explanation of what is known as Gauss's law, which we will discuss or which will be used in our module, in module 6. Okay, so module 6 is all about charges and electric field, which means that we are studying what happens to the space when we place a charge. So base doon sa concept natin, if you have a space and you place a charge in the space, it will disrupt or modify the space surrounding that particular charge that we place. And that change in the space around it is what is causing the electric field. Now, the electric field is that space would provide or will exert a force, the Coulomb's force, on any charge that is placed in the region or the vicinity. And that is the reason why when you place, let's say, a positive test charge in an area with another charge, then that test charge will experience a force. Depending on the sign, if the charge creating the region is positive, the positive test charge will experience repulsion. Kasi di ba sa Coulomb's law or sa theory, if you have two positive charges or similar charges, they would repel one another. Now, if the region, no, or the charge creating the region or the field is negative, the test charge that you place close to the region would be attracted, simply because you'll have unlike charges, and if you have unlike charges, they should attract one another. Therefore, the force will be into or towards the other charge. So those principles are discussed in the module. Now, the Coulomb's law, which states the magnitude, no, of the force, be it attraction or repulsion, is provided using the inverse square law, wherein the force is equal to a constant times the product of the charges and inversely proportional or over the square of the distance of separation. So which means that the force will be larger if the charges are larger. Kasi you multiply the two, no? Yung Q. If you have more than two charges, then what you can do is determine the force between the charge and determine another force for the other charges. Now, yung over r squared means that the farther the charges are from one another, the lesser would be the force of attraction or repulsion. Okay, so that's Coulomb's law. Now, in Coulomb's law, you look into the amount of charges, yung Q mo, as well as the distance of separation. Okay? Now, it's good. You can solve problems using Coulomb's law. Now, but there are situations in which you don't know the charge, how many charges are creating the field. So it's possible na marami kang charges, no, in a certain region of space. So, ibig sabihin, if you put a test charge close to the vicinity, you have to compute for the force exerted by each of the charge on the particle. Diba? Ganon. So, parang ganito, kung isa lang, madali na isa lang yung charge, ganyan, say positive yan, and then you have a test charge that you place on the object, kasi nandito siya, ayan. So kung magkaiba ng sign, magkakaroon ng attraction. Therefore, yung force mo will be towards, pag ganyan. Magkakaroon ka ng force pag ganyan. Kasi na-attract, no? Okay, so kung meron kang marami, let's say dalawa, no? Dalawa na charge mo. Okay, naging dalawa na siya. Dalawa na. Ganyan. So the force now being exerted on the test charge that you place will not be the same as the original line that you see. So ano mangyayari? You'll have now two na forces. Ganyan. Okay? So dalawa pa lang yan. Now what if you have a charge that is not, kung hindi siya tawag dito, hindi siya positive, let's say negative. Okay, ganyan. So what will happen? The force acting due to the charge, no, will cause a different force, which is repulsion. Okay? So, if you have many distribution of charges and you want to know the force acting on a test charge that you place in the vicinity, it would be hard for you to compute because of the variation of this one. Okay? And if you do that, also, no, each of these charges would have its own electric field. So what will happen if you have the charge if with its own electric field, okay, like that. So for example, this one will have its own electric field. This one will have its own, and this one will have its own electric field. And the direction will depend on the sign. Kung positive, no? Meaning kasi ang electric field mo is in the same direction of the force. So kung positive siya, so ang direction ng field mo is towards the dito sa particle paloob. Kung negative naman, away. So magkakaroon ka ng variation in the direction of the electric field. And if you want to take the true direction of the field, you have to get all of the charges and all the fields together. Kasi vector naman yung field. That's the problem when you deal with this type. Okay? This type of field na iba-ibang charges. No? So hindi na madaling gamitin si Coulomb's law in this case. So ano yung pwede mong gawin? What you can do is consider mo yung field, no? So ang isipin mo yung field mo would be something like this. Okay? And then yung distribution mo nito kasi di ba pwede mo i-sum up sila yung lahat ng charges dito could become or could be represented by only one charge, no? Which is somewhere. Kung depende dun sa kanya, pwede mo i-consider na isa lang siya. Ganyan. And each of this, no, would parang isa na lang siya na charge distribution. And therefore, magki-create siya ng electric field like this. Okay? So depending again sa direction nito o nung net charge mo dito kung positive or negative, the field that will be created, yung direction niya will be going out or going in. Now if we assume it to be going out, assuming na going out siya, let's say ibig sabihin ay kung going out siya, that means na positive charge yung net charge mo sa loob. So what will happen is, kung isipin mo, parang meron kang ngayong mga field going out like that. O ganyan. No? And in that case, it is not very easy to determine the field. Okay? Kasi sabi nga, if you consider yung sa Gauss, yung nagko-cross na field on nagko-cross na forces ng field lines on the surface, yung value niya will depend, yung strength niya will depend on the distance from the point. Kung malayo, mas mahina, kung malapit, mas malakas, as well as kung perpendicular ba yung surface doon sa doon sa field, no? Kasi yung may effect dito dapat perpendicular sa field. So medyo mahirap na i-compute or i-determine yung charge mo dito as well as the field. So what happens is, pwede mong gawin is, yung naisip or na-discover ni Gauss is, you can make things simpler. No? Pinapasimple lang niya. Paano yon? So if you have the charge na ganito, yung naging charge distribution, ganyan. Okay, kasi drawing natin ganyan. And you have a surface, meaning dahil iba-iba yung iba-iba yung strength, no? Kasi 'di ba charge distribution to, so it's possible na iba-iba yung strength at different areas. So ang mangyayari niyan, let's say ganito yung distribution mo, mas malakas yung field dito kaysa dito. Okay? Mas malakas. So ibig sabihin mas malapit. Kasi itong line na to parang equipotential line. Yung ibig sabihin ng equipotential line na to is yung potential niya or yung strength ng field mo pareho on the parang ano on the circle. So think of it as yung contour ng let's say sa bundok. Kung nakakita ka sa mapa na isang bilog na ganyan, that means na yung height noong point na yon do sa map ay pare-pareho. Okay? So the field strength for that yung circle na iba yung shape or nung closed loop should be the same. Okay? So mas malapit to, okay? Ibig sabihin mas malakas dapat yung field, yung force mo dito kaysa dito at this time. Pero yung potential mo would be the same. Ngayon, so pag determine mo yung ano, yung charge dito, ang pwede mong gawin is just count the ano or gamitin mo yung flux. Bibilangin mo lang yung dumadaan, no? Yung dumadaan na parang E-line, electric field line sa kanya. Ganyan. Ganyan. Yung dumadaan sa kanya. Yung nagko-cross do sa surface mo. Ayan. Kaya nga, babalik tayo doon sa same problem na pag kinumpit mo siya, mahirap. Kasi nga, hindi lahat ng ano mo, ng electric field lines mo ay perpendicular doon sa surface na inaalam natin. So, ginawa ni Gauss is, why not create another surface which is much easier to compute. So, dito niya naisip na, let's say, gawa tayo ng sphere rather than gawa tayo ng ano, irregular shape. Gumawa tayo ng sphere. Kasi pag sphere, alam mo yung ang center ay yung distribution ng charge and then alam mo yung r distance na fixed siya kasi nasa center yung ano mo yung isipin mo isang point lang yon, so yung r mo nasa center ganyan. So ngayon ang nakita niya pag binilang mo yung electric field lines na nagko-cross doon sa surface na hinahanap natin, yung kung dinedetermine mo yung field sa labas, kung bibilangin mo yan, pareho lang, no? Kasi syempre nag-go outward yan. So whatever yung electric lines, no, na nagko-cross doon sa surface, the same as the electric lines na nagko-cross doon sa circle mo o yung sphere mo. Okay? And then hindi ka na ngayon magkaka-problem when you compute yung ano mo, yung tawag dito yung electric field. Kasi if you get yung parang area na perpendicular doon sa surface ito, no? Perpendicular doon sa line, hindi siya diretso, no? Kasi magkaiba nga yung as mentioned doon sa lecture, magkaiba yung parang ano yon, yung dA, yung normal to the yung small area, hindi siya parallel dito sa ano mo, sa field mo. Therefore, kailangan kunin mo pa yung component ng surface na perpendicular, no, or parallel doon sa ano mo, dito sa electric lines mo. Okay? But kung circle siya, laging perpendicular, no? Ang kung titingnan mo, laging perpendicular yung surface area at parang element doon sa field mo, doon sa electric field mo. Okay. Pero syempre, since iba tong area nito, no? Kung titingnan mo, if you have the same field dito at dito or the same flux, mas iba yung area dito, iba yung area dito, no? So, ang mangyayari niyan, pero magiging proportional pa rin. Proportional ito dito. Okay, yung value. So, ang pwede mong gawin, rather than computing for this bigger area, you can compute the field for the smaller area, yung circle. But since proportional, hanapin mo na lang yung proportionality constant. Pag nakita mo yon, then makukompute mo na yung electric field dito sa uneven surface. So, ganun ang ginawa ni Gauss at nagawa siya ng law at nahanap niya yung constant, no, na gagamitin. Okay. So, ngayon, ang ginagawa natin to solve this type of problem is to create what is known as a Gauss. Ito, Gaussian surface, ang tawag dito. Itong parang region na dinodrawing natin, no? Hindi siya totoong object. Dinodrawing lang natin siya, closed surface siya. Okay, depende sa situation. Tapos ginagamit natin siya to compute. And of course, magdedepende ngayon siya ano yung gagamitin nating surface to determine the yung electric field. So depende yan. Kung point charge yan, usually spherical ginagamit natin. Ganyan. Pero kung ano siya, let's say piece of parang ang distribution mo ay ang area. Let's say meron kang material na hindi point o hindi sphere. Let's say rectangular or iba yung shape mo. So paano mo yon gagawin? Let's say ang ang area mo ganito na dinedetermine. Pag ganyan. Ganyan siya. Ayan. So isipin mo na ano to, parang papel, no? Plastic, sheet of paper. So yung dumadaan sa kanyang electric field, yung pinaka electric flux niya pag binilang mo per unit area should be perpendicular to the surface of this one. So makikita mo yung isipin mo na meron ka ngayong mga lines coming out na all of them ay perpendicular to the surface. Ganyan, no? Pag ganyan. So, how do you now do this? Hindi mo na pwede gamitin ang charge distribution dito sa dito sa sheet na to, itong figure na to. So, nag-exert, meron ka ngayong parang electric field in that direction. So, you can no longer use this na circle. Bakit? Kasi pag ginamit mo yan, hindi mo ma-enclose properly, iba yung shape niya, no? Hindi mo somehow simplify. So what you can do is develop or create a different type of Gaussian surface which is still regular, meaning you can compute the surface area, kaya mong makita kung alam mo yung distance from a certain point, and so on. So alam mo yung volume, alam mo yung area na parang mako-compute mo na. So pipili ka ngayon ng ganung Gaussian surface na i-apply dito sa ibang situation. So, example, ito, let's say tiningnan ko to na sa sideways, no? Looking at the sides. So, looking at the sides, you'll have something like this. Pag ganyan na siya. And then the electric field na nakikita mo crossing the surface would be perpendicular to that surface. Kung makikita mo, yung field mo, magiging ganito na siya. Perpendicular. Ganyan. No? Ganyan na siya. Kasi tinignan natin yung looking at the side of this. So ang makikita mo, ganyan na, uniform na paganyan. Okay, so what you can do now is, why not create a surface, create your Gaussian surface to still determine or compute for yung electric field. Encompassing this, na mas madali. So ano yung naiisip mo dito? Ang pwede mong gawin dito would be, ano siya, parang instead na ganyan, ang isipin mo, gagawa ka lang ng surface na ganito. Parang ganyan. Para siyang cylinder. Gagawa ka ng parang cylinder. Okay? Na ganyan. Of the radius, yung cylinder mo, yung flat side niya would have an area na parang area ng circle. Ito rin, area ng circle. Okay. So, with this, alam mo na, alam mo tong ma-determine tong area na to, kasi alam mo naman yung equation nito, alam mo rin dito, the same lang siya. And if you compute for yung number of lines crossing yung perpendicular to the surface, you'll notice na only itong part na to at itong part na to ang perpendicular dun sa lines. Yung surface around the cylinder, yung paikot, no? Imagine ito yung surface ng cylinder mo. Lahat ng surface niya ay parallel doon sa electric field line. That means na if you determine the effect or the tawag dito, yung number of lines crossing, no? There will be no line crossing on this surface. Magko-cross lang yung line mo doon sa dalawang circle. But you know this very easily to get the area of this circle, no? So magiging defined ngayon yung pag-determine mo ng number of lines crossing perpendicularly to the surface. But that's what we need. We want to know the area, no, where our E line are crossing perpendicularly to that surface. So, ano nangyayari nito? Pwede mong mag-create ka ng region just to make it easier for you to solve. No? Gagamit ka ng something na figure that will make things easier. Dahil, sabi nga ni Gauss, yung number of lines, no, for that particular surface would be the same. And the strength or the value would be, yung electric field would be just proportional. Ibig sabihin, kaya mo nang makompute yung hinaharap mo for this, yung blue surface na to, by computing the ones on the green surface. Yun yung ginawa ni Gauss. Okay? So dahil doon, lumabas yung mga equations niya na pag-determine at naging ano siya, parang integral na lang siya nung ano mo. Kasi iba-iba nga yung shape. So depende na sa'yo kung ano yung gagamitin mo yung dA do sa equation. Diba sa yung E mo o yung flux mo, yung sabi sa lecture is integral, no? Surface integral of E dot dA. So yung dA mo, magde-determine pag in-integrate mo na siya, magde-depende na yon kung ano yung surface or ano yung ginamit mo na Gaussian surface doon sa particular application na yon. Pero ang gagamitin mong Gaussian surface would be something na you can easily compute kasi alam mo na yung pag in-integrate, for example, yung dA, alam mo na yung area na makukompute niya. So, ganun yung ginawa, no? Of course, kung hindi mo siya isi-simplify na ganun, medyo mahirap. If you just look at the equation, medyo mahirap siya, no? Intindihin. Pero kung iisipin mo yung ano, yung behind it, Gauss is actually making things easier for us to compute, no? Kaya lang kung hindi mo naintindihan yung mathematics, kung titingnan mo lang yung equation, then you might say it is making things harder for us. But in reality, pagpapadaliin niya yung pag-compute kasi you are provided with a surface with known or very easy to compute yung area. Kasi kailangan natin yung area to determine kung alam natin yung electric flux, mas madali natin makompute yung electric field na strength. Pag alam natin yung electric field strength, pwede na tayo mag-compute ng forces when you place charge in that particular surface. Ganun yung idea. So yun yung ginagamit doon sa Gauss's law. Bakit siya ini-introduce sa electricity and magnetism? No? Para mas madali mag-compute or mag-determine ng value ng E or ng force for irregular shape, let's say na conductors for example. Ganun yung idea. So, kung titingnan natin doon sa ating material, no? Yung dito. Ayan. Na-disconnect kasi ako kanina. So, nung nag-on ako, hindi pala automatic mag-on yung mic. Okay. Thank you for reminding. So, kung yung dinidiscuss natin na yung sa Coulomb's law. Ganyan. Tapos ito ngayon yung sa Gauss's law. So sinasabi lang dito na you can compute the electric field for a given surface if you know the area, no, of that surface na perpendicular sa kanya. And if you sum up or if you integrate over the surface, integral, you get some value. Kung uniform field siya, yung integral nito, nung dA mo, if you add all the small parts of the area, you'll get A. But since perpendicular lang siya, ang kinukuha natin, you get A cosine theta. No, where theta is the angle ng surface mo, perpendicular, dun sa electric lines na ano siya, na actually parallel sila, yung component ng area parallel doon sa E mo. Okay? So times E. Kasi E in this case would be some constant value. So for a uniform field, meaning pare-pareho yung strength mo at direction, it will simply be, if you do an integral of that, you'll just get EA cosine theta. Ayan. But then, in-extend ni Gauss yan kasi nga, yung flux mo, yung pag binilang mo, ang flux kasi is yung number of lines or number of electric field line passing through a certain area na perpendicular. Doon, nung ginawa niya yung surface niya, na pakita niya na yung flux mo would just be the whatever charge, total charge enclosed by the surface that you're using divided by epsilon sub O. Okay? So, with this simple equation na flux is equal to Q over epsilon sub 0, you can now determine the charge Q of a distribution if you know the flux. Or if you know the number of lines, electric lines passing through the surface. Kasi epsilon sub O is a constant. Ganun yung idea niya. And that makes things easier to compute, no? Dahil ito na lang yung equation mo, Q over epsilon sub O, to measure or to determine the flux. Ganyan. And in yun na nga, pag ginamitan mo ng Gaussian surface, it's very easy to compute itong flux na to. Kasi alam mo kasi ginamit mo sphere, mas madali mong makukuha yung flux mo kasi alam mo yung integral nito, mas madali. Kasi alam mong kung sphere siya, always perpendicular yung yung dA mo sa E. Tapos alam mo yung pag-compute ng integral ng dA, which is just the surface of the sphere, no? Kasi sphere yung ginamit mo. Therefore, it is very easy to determine either yung flux mo or yung E mo. Tapos, pag ginamit mo dito sa charge over epsilon sub O, madali mo nang ma-determine. Kasi given naman yung E sub O mo, constant siya. Tapos, alam mo yung Q na hinahanap mo na charge. Okay? So, mako-compute mo na siya kasi alam mo yung ito over this is flux, but then flux is this one na mako-compute mo naman using the electric field and the area. Okay? So parang mangyayari, mako-compute mo ngayon depende sa yung Q mo depende sa E or sa electric field mo. For an irregular or a different surface, no? Kasi madali yung pinag-uusapan dati dahil kung point charge lang, madali mag-compute. Pwede mong gamitin yung Coulomb's law kasi isang point charge lang yon. Pero kung charge distribution na siya, medyo mahirap ng computin using Coulomb's law. Yun yung idea. So with that, may mga sample dito which explains kung iba-iba yung yung shape na ginagamit mo. So kung circular siya, and also pinapakita dito yung iba-ibang charge distribution. Kasi kung solid sphere, iba yung pag-distribute ng charges do sa sphere. Kung hollow sphere siya, iba yung pag-distribute. Kung plane siya, parang area na rectangular, iba, and so on. But then, kung line siya, yung distribution ng charge mo ay along a wire, for example, ganyan siya. So, ang E mo would be parang siya, in all direction around the line. So, pwede ka mag-create ng a different Gaussian surface to be able to compute the E around the wire. Something like that. So, magdidepende ngayon siya. No? kung ano yung gagamitin mo. But using a Gaussian surface, it will be easier to compute. Kasi alam mo na yung property nung pag ganun yung material mo, na ganun ang itsura. Kasi alam mo na yung pag-compute ng area ng cylinder, for example, in this case. Ganon. So, ganon yung ginagawa dito sa chapter na to. Ito yung pinapakita ko kanina, kung ang charge distribution mo ay plane, ganyan, tapos ang electric field mo ay, siyempre, kung nandito yung charge mo, na isipin mo na yung charge mo hindi na point, parang ano siya, napisa, na spread siya na parang sheet ng papel. So the forces will be on both sides, no? Pag ganyan. Ibig sabihin, pag naglagay ka ng test charge dito na positive, it will be repelled pataas. Pag dito ka naglagay ng charge mo, it would be repelled pababa. So on direction ng E mo would be dito pababa, dito pataas. Ganon. So kung dito ka naglagay sa side, then wala ka dapat na kung uniform tong field mo dito, wala ka dapat na force pag ganyan. So hindi magmo-move yung charge mo parallel to the surface pag ganyan. Kasi wala kang E na perpendicular sa kanya. Yung ganon. So kung ang definition mo nitong sheet na to ay infinite, then you don't have to worry about that. Now, kung alam mo na siya, then you can use a cylindrical Gaussian surface para ma-determine mo yung mga E mo. Kasi yung part na perpendicular dito, parang dito na lang siya sa flat plane ng cylinder mo. Madali mo nang computein to para lang siyang circle, no, yung area niya. Basta alam mo yung radius. Therefore, it is easier for us to determine E na ganito. At ito nga, pag sinolve mo siya using this approach, you'll end up with sigma over 2 epsilon sub 0, yung value ng E mo, where sigma is the distribution of the charge on the surface. Yung parang Q per unit area doon sa surface mo, you end up with sigma over 2 epsilon sub 0. Madaling ma-compute yung value ng E. So at ang makikita mo dito, for a charge distribution, ganito, uniform siya, no? There's no R. Ano ibig sabihin nito? Walang R. So for a uniform field like this, na ganyan, it doesn't matter kung gaano kalayo yung mo, kung uniform siya, no? It doesn't matter kung gaano kalayo, okay? As long as, kung gaano kalayo doon sa surface mo, you get the same value of E, independent of R. Kung makikita mo dito, it just depends on the strength or the charge distribution on the surface and the constant. Okay, pag uniform field, makikita mo, which is not easy to comprehend na bakit ganon. Pareho lang ang makukuha mo kung iba-iba yung distance mo, pareho lang yung value ng E mo for a given distribution of charges. Of course, that is only true kung siya, tong plane mo na to ay infinite yung size, no? Kasi parang meron kang meron kang tawag dito, parang assumption na laging perpendicular yung mo, yung E mo dun sa surface mo. Pero kung isipin mo kung finite yung size nito, kung isipin mo dun sa sides, hindi na perpendicular yung E mo sa surface, no? Kasi dito sa side na to, maaring siya, either pag ganyan or pag ganito, depende sa situation, no? Pwedeng paliko na yung field mo. Therefore, hindi na to mag-obey dito. Kasi ang assumption dito, lahat ng E mo parallel to one another. Walang nagde-deviate, no? Walang liliko para ma-compute mo. So this is true if you have an infinite, parang infinite na i-assume mo sa edges ng material mo still perpendicular yung E mo. Okay. So with that, you can now use also Gauss's law, for example, to determine the value of total charge of an area by just enclosing. I-enclose mo lang yung region of space mo, tapos kukumpitin mo yung total charges mo. In this case, meron kang -6, tapos plus 4. So, kukumpitin mo lang yung ang Q mo dito is minus 2, di ba? Kasi may 6 ka dito, may 4 ka, to minus 2 microcoulomb. So, yun ang Q mo over epsilon sub 0, no? Kasi you will get the flux. Kasi alam mo yung flux is equal to Q over epsilon sub 0. So, makukompute mo na yan. Ikutan mo lang siya. Tapos bilangin mo yung total charge or add mo yung total charge, no? Positive or negative. You don't even have to look into ano yung direction ng field. I-add mo lang yung amount of charges and get the net. And then use that net charge divided by epsilon sub 0 and you get the electric field of that region or of electric field contributed by the different charges. Ganun yung idea. So with that, you can now do problems of different shapes. At ito nga yung nasa problem set na gagawin nyo. Ayan. So yun yung sa Gauss's law. Now, if you have questions or medyo nakakomplicate pa kayo, please panoorin nyo yung video, lalo na yung sa Yale na video, discussing this, no? So, kung titingnan mo, meron ditong mga videos, marami, about that idea. Please, kung medyo malabo, please go over this video to understand more on this one. Also, I'll include this later, yung sa Yale video, yung pinakita ko sa start ng klase natin, which discusses yung Gauss's law. Okay? So, kung may question kayo dito, please send a chat message to me kung meron kayong tanong, no, para dito. So, bali yung chapters natin, yung dito sa module 6, yung una is about yung ano lang, concept ng charges, positive and negative charges. So, simple lang doon kasi positive charges or similar charges will repel one another. Charges that are different will attract each other. Ganon, yun yung una. And with that, you can have attraction and repulsion. Tapos yung chapter 2 deals with parang quantitative, how much is the force exerted kung charge na yung body mo. And sabi ni Coulomb, yung force na in-exert sa body mo would be proportional to the product of the charge and inverse to the square of their distance of separation. So yung K mo na constant, which if you derive it, you'll end up with 1 over 4 pi epsilon 0. No, yung K mo. So yung epsilon 0 constant yan. So yung 1 over 4 pi epsilon 0 is a constant. May kanyang value ng K, no? Which is 9 times 10 to the 9. Tapos yung epsilon 0 mo is 8.89 times 10 to the minus 12. Yung isa, 8.9 times 10 to the 9. Okay, yung K mo. Tapos yung epsilon 0 mo is 8.9 times 10 to the minus 12. So, 1 over 4 pi epsilon 0, that's a constant that will determine the force. No? Yun ang constant mo. So, pag minultiply mo siya ng charge in Coulomb, nung dalawang particle na nag-act over their distance of separation na naka-square, you can determine the force. Quantitative na yon. So, yun yung Coulomb's law, particularly for point charges. No? Parang iisipin mo mga points lang siya, walang area. Ngayon, kung charge distribution na siya, let's say for example, dito sa drawing na to, nag-distribute yung charge mo on a sphere, although hindi to sphere, so the charges will be on the surface, yung sphere mo. So, hindi mo na pwede gamitin yung Coulomb's law. Kasi ang assumption ng Coulomb's law, point charges na siya. So, paano? Gagamitin mo na yung Gauss's law. Kasi sa Gauss's law, kaya mo nang ma-determine given yung electric field or yung electric flux na yun yung number of field lines crossing the surface, makukompute mo na yung charge sa loob, yung net charge. Kasi may equation na nga si Gauss na yung flux mo would be equal to the enclosed charge inside over epsilon sub 0. Parang ganun yung idea. Okay? So actually yung Gauss's law is marami siyang implication. One explanation is if you are in an aircraft, say sa eroplano, so nakasakay ka sa loob, tapos nasa ano ka, lumilipad kayo. Tapos tinamaan ng kidlat yung eroplano. Mamamatay ka ba sa loob? O makukuryente ka ba pag nasa loob ka ng ng eroplano? Kung totoo 'yon, di marami nang namatay dahil sa lightning, no? Na pag kasi bawat lipad ng eroplano, may lightning na tatama sa kanya. Kasi bakit? Pag lumilipad na yung eroplano do sa taas, magrarab yung body niya sa air at magki-create ng ng electrostatic force, no? O ng charge. So magpo-produce ka ng lightning. Actually, merong yung lightning kung naipon na siya, kung hindi siya naipon do sa cloud, medyo hindi mo makikita. Pero what's happening is you're being stricken by lightning all the time, na mahina lang. But how come na hindi namamatay yung mga pasahero due to the lightning? Kasi sabi ni Gauss, okay? Sabi ni Gauss, yung airplane mo para siyang Gaussian surface. So pag in-encircle mo siya, okay? Binilugan mo, the charge is the charge, no? Yung enclosed by the surface, pag ganyan. Kaso pag gantong circle, ang charge mo hindi siya magstay doon sa center. Magdi-distribute siya doon sa surface, nasa labas. So pag nag-draw ka ng Gaussian surface sa loob ng sphere mo, 0 yung makukuha mo. Kasi wala kang net charge sa loob. Kasi yung charge mo distributed sa labas. So pag may tumamang kidlat, yung lightning kasi, di ba, parang electrostatic discharge lang yon. Pero actually, transfer of charges yon. Magbi-build up yung charge do sa surface ng eroplano mo. Pero internally, wala. So ano mangyayari? Hindi ka makakuryente sa loob. Parang gano'n ang mangyayari. No? Ngayon, kung nasa labas ka, what will happen, although hindi mo magagawa yun, nasa labas ka ng eroplano, no? Madadala ka ng hangin. So kung nasa labas ka, what happens is you become part of the surface. And so the charges will be distributed to the plane and as well as your body. And since there's no potential difference between your body and the plane, kasi nakadikit ka doon, so what will happen is, hindi ka makukuryente rin. Parang ganun ang idea. So, yung ganun ay ginagamit na natin what is known as a Faraday cage. Yung ganun. So, ngayon, ang suggestion nila, let's say, pag daw kumidlat, let's say, na-stranded ka sa gitna ng parang bukid or highway na walang matataas na puno, and then kumikidlat, what is the best way na gagawin mo para hindi ka tamaan ng kidlat? Tatakbo ka sa field, magtatago ka sa ilalim ng puno. Okay, so hindi ganon. Dapat either mag-lay down ka sa surface flat para hindi ka maging pointed object na sa'yo magdi-discharge yung lightning, or you can stay inside your car. No? Pag nasa loob ka ng car, enclosed yung surface mo, then ang charge pag tinamaan ng kidlat will be distributed on the outer surface of your car. Internally, hindi ka makukuryente. Parang gano'n. So, gumagawa sila ng Faraday cage, for example, sa mga research na gumawa sila ng malaking Van de Graaff generator na may kumikidlat sa labas, no? Nakukuryente yung labas, pero may tao sa loob. So yung surface na to, pine-prevent niya yung ma-electrocute yung tao sa loob, kung malaki to, kahit na mayroong mga static discharges sa labas. So there are videos like that showing na merong tao na naka-engage naka-engage, pero may mga kidlat na tumatama sa kanya, hindi siya namamatay. Dahil internally, walang charge. Walang net charge sa loob. So ganun yon. So please review this and tingnan nyo yung ganyan. Now, next meeting sa Tuesday, I will have some more on the discussion nung part na to. So I'll do some problem solving. But please tingnan nyo na yung ano, yung sa problems dito, yung sample problems dito, dito. And then I'll try to solve some of this, itong mga to. Ayan, some of them sa next meeting natin para maintindihan natin how to compute for the values ng mga charges and so on. Okay? But please read through this, including yung ano, yung mga videos. Panoorin nyo. Kung may question kayo, you can email, no? Of course, yung mga tatanungin nyo, syempre, pag sinearch nyo dun sa ano, sa material natin o dun sa video, masasagot naman, no? Yung mga tanong. But if you still have questions, pag binasa nyo tong part na to, medyo malabo sa inyo, tong part na to, ganyan, paano nangyari yan, etc. You can send an email to me and I'll try to answer you or explain to you in simple terms. Or maybe point you to a video that will explain kung anong hindi mo maintindihan.